This is the third and final installment of the 2045 laboratory final review. First thing we're going to look at is gas loss, and here the main thing you're needing is pressure times volume equals the number of moles times a constant we call the ideal gas constant. It depends on the units you're using, and times the absolute temperature in Kelvin. PV equals nRT. This is one of those formulas you'll get to know and love. And the neat thing about this is it can be rearranged. If you're holding something constant, you can do something like, so let's say we were holding temperature in moles constant. You could say that this is equal to a constant, and then say P1 V1 equals nRT equals P2 V2, or you just get rid of the nRT entirely and say P1 V1 equals P2 V2, which basically says as the pressure increases, the volume has to decrease proportionately. So let's try something a little bit different. Let's say we're only holding moles constant, and everything else can change. So if the moles are constant, it's nR, so you'd say PV over T equals nR equals, and if we say 1, 1, and 1, we'd say equals P2 V2 over T2. And it so happens in this case that T2 is what we are trying to solve for. So what do? We multiply each side by T2 to get it on top. Get rid of that. And then multiply each side by T1 to get it out of this side. Gets rid of that. And now we divide each side by P1 V1. So and here we go, P1 V1. And now it looks a little messy, but and that actually gets rid of these. But if you look at what doesn't get canceled out, I have T2, and everything else on this side is canceled out, equals P2 V2 T1 over P1 V1. So let's go ahead and rewrite this in a little bit neater form. T2 equals P2 V2 P1 over P1 V1. And notice pressure cancels with pressure, volume cancels with pressure in terms of units, and you get temperature as a result. Let's go ahead and identify what these are and then plug them in. So what is T? Let's start out with T1 is 81 degrees Celsius, and we have to calculate that out. I'll calculate up here. 273 plus 81. 3 plus 1 is 4. 7 plus 8 is 15. And it looks like 354. 354 degrees Kelvin. And T1 equals the initial, which is 120 kPa, kilopascal, and next while we're with the ones, say V1 equals 45 liters, and now we have T2 equals 50 kilopascal. Up here, 50 kilopascal. T little a, kilopascal. And now we'll basically take these values and stick them into this equation right here. I am going to get rid of that mess. We've done the calculation. Let's just erase all this. Good. Okay, let's go ahead and put this in here. This is equal to P2, which is 50 kPa. V2, what is V2? Oh, I forgot V2. V2 equals 40 liters. Times 40 liters. And then you have T1 times 354 Kelvin. Over P1 is 120. And V1 is 45 liters. Okay, now we'll just cross things out and let it go. Where are we? Let's see what we get. In other words, do our unit analysis to make sure everything's good. We have kilopascal, cancels out with kilopascal. Liters cancels out with liters, and sure enough, I have Kelvin. I have to convert it to Celsius because they want Celsius, but hey, that's a good start. Go ahead and calculate this guy out. And I get 131 Kelvin. So when I calculate everything out, I get 131 Kelvin. Okay, so when I get that answer, I get so this is the 0 point, And wow, that is interesting because that's actually way less than 0. It's super cold to get this to be the case. 3 minus 1 is 3 minus 1 is 2, 7 minus 3 is 4, and 2 minus 1 is 1. So it's negative 142 Celsius. Let's see if that's, double check it, 273. Yeah, negative 141 Celsius. That is pretty darn cold. It actually rounds to 142, it's 141.8, so it's negative 142 Celsius, which is correct, yeah. 142 Celsius, negative. Okay, let's take the next one. I have a gas that occupies 1 liter at STP. What is the molar mass of the gas? It's so at STP, which is 273 Kelvin or 0 Celsius, 1 atmosphere, 1 liter, or 1 mole, not 1 liter, 1 mole. So your ideal gas at this temperature and pressure, any ideal gas is going to be 22.4 liters. Or you could say simply that volume equals moles times 22.4 liter per mole. So moles cancels and volume in terms of that. So I should actually put N is usually referred to moles, so I say N. So N is the number of moles, and the moles is the unit that cancels, and you end up with liters. Okay. So what I want is if molar mass is mass in grams over N. So the mass in grams is 0.531. 1 over N is simply rearrange this and you say 1 over N, divide each side by N, and divide each side by V equals 22.4 liters over V, which is 1 liter. So we take 0.531 grams times 22.4 liters per mole divided by 1.00 liters. Now liters cancels with liters, and you end up with grams per mole, which is the units of molar mass. So it's essentially 0.531 times 22.4, since 1 dividing by 1 doesn't do anything. times 20. And that is 11.9. That is 11.9. How many sig figs do I have? It looks like 3 sig figs, so it's 11.8944, so that's 11.9 grams per mole. So that's my final answer. Let's keep going. Find the mass in grams of 2.50 liters of oxygen of any of these gases. I'm going to do one of these. Let's do nitrogen and at STP. So I have 2.50 liters times 1 mole per 22.4 liters times the molar mass of the gas, which is 28. Oh, close enough, 28.01. And I get 3.1. How many sig figs? Looks like 3.13 grams. Now you can do it for the rest of them, but that's what you do. Notice this value will stay the same, and you're just changing in the molecular weight. 2 for hydrogen, 16 for oxygen, and so forth. How many liters will 5.0 grams of gas occupy? Well, it's the same idea. Here I'm talking about multiplying here instead of dividing. So I have 5.0 grams times 1 mole per 32 grams times 22.4 liters per mole. Look at what cancels. And we have grams with grams, moles with moles, and what do you know? I've got liters. Let's see what we get. Yep, 3.5. Double check it. Done. Let's keep going. calorimetry. So calorimetry was lab 10, and here we have a piece of metal. 500-gram piece of metal changes 7 degrees Celsius when heat is added. How much heat energy produced this change in temperature? And it is the specific heat of iron, if I remember right, is 0.46 joule per gram Celsius. Double check it. Specific heat of iron is 0.45. That's a little off. In joules per gram degree Celsius. Oh, that's... And this is for 100 grams. Okay, joule, 0.55 joule per gram degree Celsius. Perfect. So we have so 500 grams times 7 degrees Celsius times 0.45 joule per gram degree Celsius. $15.75, 1,000. How many 7 degrees Celsius? So my first answer would be 1,575 joules. Notice I only have it's not 7 point something, it's 7 degrees Celsius. So I got to round all the way to the thousands, so it's 2. That would be the most correct answer because of the 1 sig fig. Okay, when 300 calories of energy is lost from a 125 gram object, the temperature decreases by 45 degrees from 45 degrees to 40 degrees Celsius. What is the specific heat? Well, delta T. So we would say, so this is basically what I'm saying, and Q equals mass times specific heat times delta T, so specific heat equals Q over mass times delta T. That's joules per gram degree Celsius, and that is equal to negative 300 calories per 125 grams times negative 5 degrees Celsius. and of course 5.0 to be exact. And of course the negative signs cancels here, so it's 300 over 120 over the quantity 125 times 5. And I got 0.48 calorie. So we have here 0.48 calorie per gram degree Celsius. If you wanted to do that in joules, you'd simply do 4 times 4.184 joule per calorie, and see what we got. And that is 2.0. It's 5. So it's 2 sig figs. 5.0 is what's limiting degrees, is what's limiting the sig figs, so it's 2.0 joule per gram degree Celsius. Okay, let's keep going. And when 100 milliliters of 1 molar sodium hydroxide is added to 100 milliliters of 1 molar calcium hydrogen chloride in an insulated container, the temperature rises from 21 degrees Celsius to 34.6 degrees Celsius. And there's the equation. Calculate the enthalpy change for the neutralization reaction. So we would take 100 mil, or 100 mil and 100 mil. So you basically have 200 grams H2O. And you have 34.6 minus 21.0. 6 minus 0 is 6. 4 minus 1 is 3. 2 minus 2 is 1. So it's 13.6. And that's a positive 13.6 degrees Celsius. And of course, specific heat is 4.184 joule per gram degree Celsius. So when we put everything together, what we want is Q equals 200 grams. That's mass times 4.184 joule per gram degree Celsius times 13.6 degrees Celsius equals 11,380. And that's a lot more sig figs than I need, but and that is calculate the reaction. So the water is getting hot. That means heat is leaving the hydroxide and hydronium, and therefore the delta H, the enthalpy change, is a negative, because if you think about it, you have the reaction, you have the water, and heat is going from the reaction into the water, so that is a negative. So it's a negative 11,380 joules. Calculate the enthalpy change per mole of NaOH. Well, we have 100 milliliters times 1 molar. So that's 0.1 mole. So we just take negative 11,380 joules over 0.1 mole. That would be 113,080. I guess that would be. So 113,800, which is not correct for the neutralization, but hey, it's what we get. Calculate the wavelength in nanometers of the line of hydrogen spectrum corresponding to electron transition from n equals 5 to n equals 3. The other one is calculate the wavelength in nanometers of the line spectrum of the hydrogen spectrum corresponding to electron transition from n equals 5 to n equals 2. Okay. With a couple of things we need. Nu equals C over lambda, and or lambda equals C over nu is 1. And then we have E equals H nu, and since nu is equal to C over lambda, you could say equals H C over lambda. So we're sort of taking this equation and putting it in here. And this is actually what we want to do because we're interested in lambda. This is going to give us the lambda in nanometers, and then we're going to get the lambda in meters by dividing by 10 to the 9th, essentially. So we have therefore lambda equals HC over E. And I'm trying to find E. So what is E? It is 2.18 times. So the energy of the photon, 2.18 times 10 to the negative 18th times 1 over 3 minus 1 over 5. That's going to give us a positive number. And here's what I'm going to do. It's easier to work this way. And this is so a third minus a fifth is 0.133, and then I should say equals 2.18 times 10 to the negative 18th times that value. And that gives me 2.91 times 10 to the negative 19th. Oh, shoot, I'm wrong. This is squared and squared. Oops, that's 3 squared minus 5 squared. Cross this out, it's wrong. Don't make that mistake. It's not it's the square function, and I don't know how I forgot that. So this is completely wrong. So this 1 over 3 squared, I can just replace that with 1 over 9, right? One over 9, and 1 over 5 squared is 1 over, well, get rid of the squared, it's 1 over 25. Easy enough. Now, let's Alt-Tab over to this thing, get rid of this, and call it 1 over 9 minus 1 over 25. It's going to make a big difference. Let's see what we get. Yeah, so that's 0.07, and this is 1.55 times 10 to the negative 19. So now I just go over here and say lambda equals 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8th meters per second over 1.55 times 10 to the negative 19 joules. Notice that joules cancels with joules, seconds with seconds, and gives you meters. So let's see what that is. That's 10 to the negative 34th. Times 3 times 10 to the 8th divided by, and I'll just divide by this cell here. That does it. So that is 1.28 times 10 to the negative 6th meters. Again, 1.282, yes, so 1.28 or 1.28. This wavelength is infrared, so we don't count it as nanometers. We actually count it in microns, so a micrometer. So generally infrared light, we call the wavelength microns. It, of course, would be 1,280 nanometers if you wanted to change it that way, but we shall use those because it's easier to use microns or millionths of a meter. Okay, calculate the wavelength, the hydrogen spectrum, electron dropping from the 1 equals 5, n equals 5 to n equals 2. Hey, we can just change 9 to 4 and we've got it. All we have to do, that pretty much done the same equation, except in here instead of 9, I take 2 squared, which is 4, and see what we get. Get a much bigger number here, 4.58 times 10 to the negative 19th, and when you do that, you get 4.34 times 10 to the negative 7th, or 434 nanometers. That would be blue-green light. Let's take a look at this. How would we do this? So equals 2.18 times 10 to the negative 1/8 times 1 over 4 minus 1 over 25. That's, again, 2 squared and 5 squared. And now when we calculate that out, that is, what is it again? 4.58 times 10 to the negative 19th. 4.58 times 10 to the negative 19th joules. Then we put that into the equation. Lambda equals 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8th seconds over 4.58 times 10 to the negative 19th joules. And it gives us, when you're done, 4.34 times 10 to the negative 7th meters. Okay. Now for the fun stuff. These are, in order to get a good valence shell electron pair repulsion theory structure, you have to have a good Lewis structure. So here I have 4 plus 7 times 4 equals 32. This is 28 plus 4 is 32 electrons. Silicon has more ways to bond than chlorine, so silicon is in the middle. And you have bonds to Cl, 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 Cl. And we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 30, 28, 30, 32, and we're out of electrons. Everything has an octet. Formal charge, you have 1, 2, 3, 4, 5, 6, 7. 7 minus 7 equals 0. Silicon is in the row with carbon, so you have 4. 1, 2, 3, 4. 4 minus 4. So you have 4 different things attached. That, of course, is tetrahedral. And this would be 4 different hybrid orbitals, so it would be sp3. Okay, pf3. And here you have phosphorus is 5 plus 21 equals 26. Phosphorus is definitely in the middle since fluorine can only bond with one thing, really. So I have phosphorus, fluorine, 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 like that, and you go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 2 on the phosphorus is 26. There are 3 things attached here, but there's 1 lone pair, so actually 4 things attached, so it's in electron geometry is tetrahedral, molecular geometry is trigonal pyramid, and it's still in sp3 hybrid. The non-bonding pair is in a hybrid orbital, and all the phosphorus fluorine bonds are in hybrid orbitals. So that's 1, 2, 3, 4 hybrid orbitals. It has to be sp3. Okay, NH3 is going to be the same as PF3. I'm not going to deal with that. SCl2 is basically going to be the same geometry as water. Let's take a look at something different, like xenon tetrabromide. So here I have 8 and 28. (36 electrons). Xenon has to be the central atom. And then you have I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and I've got everything with an octet, and I still have 4 electrons more to go, so I have to put those 2 electrons here on the xenon. So that's going to give me, of course, hypervalent xenon, but that's necessary. This is 1, 2, 3, 4, 5, 6, 7, so that's 0 for each of the bromine. And xenon is 1, 2, 3, 4, 5, 6, 7, 8. So that's 0 for the xenon. So our formal charge works out. We have all the electrons accounted for. If I didn't have these electrons in, the whole mess would be a positive 4 charge, which would be sort of crazy. So we have, if we look at the groups that we have attached to this atom, they are 1, 2, 3, 4, 5, 6. So it's clearly the e.g. octahedral. Molecular geometry is square. Molecular geometry of square planar. Okay, let me see if there's more interesting stuff. I'm not going to spend a lot of time on stuff that's fairly simple. I want to try to find stuff that's going to give you trouble. This 12 and 14 may be interesting. Let's do all of these. Not so hard. Sulfur is 6 plus 6 times 7. Wow. So that's 42 plus 6 is 48. Sulfur has to be in the middle, and we have 1, 2, 3, 4, 5, 6. We have 2, 4, 6, 8, 10, 12 of the 48. Now we have 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48. All the electrons are accounted for. I have 6 bonds on the sulfur, each attached to the atom, so it's, of course, octahedral. And I forgot, of course, this one I wanted to go back to is octahedral square planar, and it is sp3d2. And this, of course, is also sp3d2. And chlorine pentafluoride, again, 5 times 7 is 30 plus is 35, plus 5 is 40. Chlorine is in the middle. And we go 1, 2, 3, 4, 5. And that's 2, 4, 6, 8, 10, 12, 14, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Oh, it's 42, not 40. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. And that is 36, 38, 40. Of course, what I'm saying is 7 plus 35 equals 42. I miscounted the electrons. So I need 2 more electrons, which is right here. That's 1, 2, 3, 4, 5, 6 groups. 6 groups is octahedral. sp3d2 molecular. This is G. Molecular geometry is square pyramid. Oh, let's see. That's a long process anyway. TeCl4, tellurium is right under oxygen. So we would have 6 plus 4 plus essentially 28 equals 34. Tellurium 1, 2, 3, 4 Cl, 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 Cl. Now we have this looks like a 6, but it's actually a chlorine. Anyway, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everything has an octet, but we have 2 electrons we have to put on that tellurium. So we have 1, 2, 3, 4, 1, 2, 3, 4, 5 electron groups. One is a non-bonding pair, so trigonal bipyramidal, that's the electron pair. Molecular geometry is well, trigonal bipyramidal with 1 missing is a seesaw, and structure, and it is sp3d, not sp3d2, but sp3d 1, 2, 3, 4, 5 things, hybrid orbitals. Finally, xenon difluoride, that's 8 plus 14 equals 22, that's a little bit fewer. And we have xenon, of course, in the middle, fluorine, fluorine, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And of course we have to have another one there. So it's 1, 2, 3, 1, 2, 3, 4, 5 electron groups. So which is pyramidal, trigonal bipyramid. It is 2 atoms, so it's molecular geometry is linear, and it's sp3d again. Basically, you're looking at this is sort of an odd one, a fluorine, this is xe, not x, xe, and then you have a non-bonding pair, and back, and another non-bonding pair here. So around the center. All the equatorial ones are non-bonding, and then 2 fluorines. Okay, that's it.